Hello everyone. Today, I will present our work, Invisible for both camera and LiDAR, security of multi-sensor fusion-based perception in autonomous driving under physical world attacks. My name is Ningfei Wang, a second-year PhD student from iSCART Research Group at UC-Irvine, advised by Professor Qi Everett Chen. My co-authors are Yulong, Chaowei, Dawei, who are my co-first authors, Jin, Ruigang, my advisor Alfred, Mingyan, and Bo. This is a joint work among UC-Irvine, University of Michigan, Arizona State University, UIUC, Nevada Research, Baidu Research, and Inception. Recently, autonomous driving or AD vehicles are increasingly deployed on public roads. For an AD system, perception is no doubt one of the most critical tasks for safe driving. Among various perception tasks, the most important and safety-critical one is in-road obstacle detection, such as detecting front cars, pedestrians, traffic cones, or barriers. Error in such tasks can directly lead to violent crashes. For example, the Uber accident in Arizona and the Tesla accident in Taiwan. Due to such direct safety impact, various previous work have studied the security of AD in-road obstacle detection. However, all these existing work are limited to attacks on a single source of AD perception. For example, camera or LiDAR-based AD perception alone. By contrast, production high-level AD systems such as Waymo, GM Cruise widely adopt multi-sensor fusion or MSF-based AD perception. Different sensors have different sensing capability. Thus, the core idea behind MSF is to leverage the strengths and compensate the weakness of these sensors to achieve overall higher accuracy and robustness. So far, the most popular MSF fuse sensor data from LiDAR and camera, and state-of-the-art design are DNN-based, considering its recent superior performance. In such design, assuming not all perception sources are or can be attacked simultaneously, theoretically, it is always possible to rely on the unattacked source to detect or prevent such attack. Such basic security design assumption is believed to hold in general. That's why MSF is widely recognized as a general defense strategy against the existing attack on AD perception. However, if we look back, all such conclusions depends on this very basic security design assumption. This does naturally lead to a fundamental research question. Can such basic security design assumption actually be broken, especially in practical AD settings? To answer this question, there are several research challenges to address. First, lack of single physical world attack vector effective for both camera and LiDAR-based AD perception. Second, need to definitively synthesize physically consistent attack impact onto both camera and LiDAR. Third, need to handle non-differentiable pre-processing steps in AD perception. Let me detail this in the following slides. First, let's talk about the problem formulation and attack goal. We targeted on physical world attacks vector for high practicality and realism. Considering its basic security design assumption, we aim at designing an attack that can effectively attack all perception sources used in the MSF-based AD perception, which means camera plus LiDAR for today's popular design. This allowed us to directly challenge the basic security design assumption, and for the first time allowed us to gain a concrete understanding of how much security guarantees the use of MSF can fundamentally provide as a general defense strategy for AD perception. As for our attack goal, we aim at fooling the MSF-based AD perception in the victim AD vehicles to fail in detecting a front obstacle and thus crash into it. To achieve this, the very first challenge is the choice of attack vector. In our case, it is ideal if we can find a single physical world attack vector effective for both camera and LiDAR-based AD perception, which can save attack deployment costs and thus improve the practicality and stealthiness. However, currently no previously used attack vector showing effectiveness for both. For instance, adding color pattern to obstacle or road surface can affect the camera but cannot affect LiDAR. And shooting laser have shown to be effective for LiDAR-based AD perception, but its effectiveness for camera-based AD perceptions remain unclear. To address this, we identify adversarial 3D object as a physical world attack vector against MSF-based AD perception. Our insight is that different shapes can affect both point position changes for LiDAR and pixel value changes for camera. Such an attack is physically realizable via today's 3D printing technologies. Such an attack can also achieve high stealthiness by mimicking a normal traffic object, such as traffic cone or barrier, but with broken look or weird-looking rock. To achieve our attack goal, the attacker can place an object on the roadside to trick the victim AD vehicle to crash into it. To cause serious crashes, the attacker can fill a 3D printed object with dense materials, for example, the granite or metal, to make it harder and heavier, or leverage the semantic meaning of certain road object types, such as the traffic cones. For example, place some nails or glass debris behind an adversarial traffic cone object, so that failing to detect it can lead to tire blowout of a target AD's vehicle. Before jumping to our design details, let's first watch some video demos of our attack. The first one is in a miniature scale physical world setup, where we use real camera and LiDAR, but set up the road environment in a smaller scale. We choose traffic cone as the object type, and 3D printed the benign one and the adversarial one generated by our attack. Here, as you can see, this is the printed adversarial traffic cone. Here is a 3D printed benign traffic cone in a small scale. Left is the camera view and the right is the LiDAR view. As you can see, it can generally be detected by both camera and LiDAR. Now is the case for 3D printed adversarial traffic cone. As you can see, we put it in the same position and follow the same movement. In the camera and the LiDAR views, its pattern looks pretty similar to the benign case. But in this case, it can never be detected by both camera and LiDAR in any of these frames. We also have an attack demo using real vehicles with valid 64-line LiDAR and camera. Here, we use the box as the benign object and 3D printed the adversarial one generated from such benign shape, which end up like a strange-looking rock. Here is the 3D printed adversarial object. Left is LiDAR view and the right is camera view. Now we drive forward. As you can see, the same as the traffic cone case, it can never be detected by both camera and LiDAR in any of these frames. We also have an end-to-end attack simulation demo. Here is the road in LG SVR, an open source production grade AD simulator. And here is a vehicle running by the Apollo 5.0, an industry grade AD system. And here is the benign and adversarial traffic cone we will import. This is the benign case. Left is the simulator view and the right is AD system view. The traffic cone is here in the roadway. As you can see, the AD system can successfully detect it and safely stop before it. Now comes to the adversarial case. We put the adversarial one at exactly the same place, but in this case, the AD system can never detect it in any of these frames and thus eventually crash into it. Now let me detail how our attack design works behind the scene, which is called MSF-ADV. To systematically generate the adversarial object, we adopt optimization-based method like many prior works. Here is what we have. We have an initial benign 3D object mesh, say for a traffic cone, the point cloud, and an image of target road, and an MSF algorithm. We need to first generate the MSF algorithm input, basically the camera image and the LiDAR point cloud of target road with objects somehow put inside, and then use the gradient to update the shape of 3D object mesh to iteratively generate the adversarial variant. Here, a challenge is that we need to differentially synthesize physically consistent attack impact onto both camera, image, and LiDAR point cloud. To address this, we use differentiable 3D rendering. For example, a customized version of recasting for LiDAR and an existing technique called NMR for camera, which are both differentiable. However, with this, we are not done yet, as there is another common step before the MSF algorithm in the production designs, that is pre-processing. For example, aggregate feature calculation and region of interest filters. This raises another challenge. that we need to handle non-differentiable pre-processing step in AD perception, especially for the LiDAR side. Let me detail this a little bit. State-of-the-art LiDAR-based object detection method popularly use cell-level aggregate feature to improve running time algorithm performance. For example, let's say there are the raw LiDAR points. To generate such feature, a pre-processing step will first group them into 2D or 3D cells, and then calculate the cell-level features such as occupancy, count, height, intensity, and density. In order to calculate this feature, the necessary first step is to perform what we call point inclusion or PI calculation, which calculates whether an input point is inside a cell or not. Such a property is discontinuous by nature. To achieve differentiability, our strategy is to first design a novel and accurate differentiable function to approximate PI calculation or soft PI, and then use it as a building block to achieve differentiable computations of features we mentioned earlier. To achieve such soft PI calculation, our key idea is to estimate the probability of such point inclusion using interpolations. We tried different interpolation functions such as trilinear and tangent edge to improve the accuracy. More details can be found in our paper. We also have other designs, for example, improving robustness to different victim approaching position and angles, stealthiness, and physical world realizability. Now it's time to talk about evaluation. We evaluate 4 MSF algorithms included in 2 open source full stack AD systems, Apollo and Autoware.ai. We select 3 object types with 100 real-world driving scenarios from PD dataset. For the effectiveness, we achieve over 91% success rate across different object types and MSF algorithms. We also evaluate the robustness against different victim position and angles, find over 95% average success rate. Also, we found high transferability across different MSF algorithms with around 75% average success rate. We also evaluate the physical world realizability, which is demonstrated before in a miniature scale and a real vehicle-based setup, and found at least 85% attack success rate across different frames. We also perform end-to-end attack simulation evaluations, which is also demonstrated before, and found our attack can achieve 100% collision rate across 100 runs. We also evaluate many other properties, such as baseline attack comparison, stealthiness, printability, and different attack settings, which are more detailed in our paper. Last but not least, we also made efforts on evaluating and discussing defenses. There are 2 general defense directions. First, DNA-based defense. We experimentally evaluate 6 popular existing input and model-level defense methods. The most effective one reduced the attack success rate to 66% without harming benign performance. However, it is not quite enough to render our attack practically unexportable in practice. This means that we need to explore more effective design in our problem settings, especially for those with strong guarantees, such as auto training and certified robustness. Another direction is to fuse more perception source. For example, fuse with more camera or LiDARs mounted at different positions or including radar in MSF. This cannot fundamentally defeat our attack, as the shift change can still simultaneously affect this sensor input. However, this may make our attack more difficult to generate, and thus could be a practical mitigation. We did responsible vulnerability disclosure, and as for April 25th, we have informed 31 companies that are deploying or testing AD vehicles. Among them, 17 have replied and started investigation. To conclude, at a high level, the most important contribution we did is to perform the first study on security of MSF-based AD perception, challenging the basic security design assumption in practical AD settings. We design a novel attack, address various challenges, conduct intensive evaluations, and also perform responsible vulnerability disclosures. With that, thank you for your attention, and I'm now open to questions.